All right, good morning, everybody. Today we're going to learn how to take derivatives of trig functions. Derivative of sine and cosine and tangent and so on and so forth. But I want to write down the shortcuts that we have so far. The derivative of a constant all by itself is always 0. The derivative of x to the n is by power rule n times x to the n minus 1. Power drops down, you subtract it from the power. And that works no matter what n is. It can be positive, it can be negative, it can be a fraction. It works no matter what. That's kind of a powerful one. The derivative of e to the x is just e to the x. It's the only function that has that property. The derivative of that function is that function itself. That's the only exponential function that we have a nice formula for. If the base is something other than the e, we'll address that later. But if it is e, if it's e to the x, derivative of that is just e to the x. The derivative, this is the prime notation, of a constant times a function. This is just a constant all by itself. This is a constant times a function. Is the constant times the derivative of the function. So that says a constant that's being multiplied times something slides through. The derivative of functions added together is just the derivative of each individual function added together. Both of these really are just a direct result of the properties of limits, because the derivative is a special type of limit. And for limits, constants slide through. You can apply the limit to each term individually. So that's what's happening here. The derivative can be applied to each individually. Same if you're subtracting. You apply the derivative to each function individually if it's being added or subtracted. And then the new ones from yesterday. The derivative of f times g. And what would be nice but not true, what would be nice is if it was just the derivative of f times the derivative of g. That would be nice, but that's unfortunately not how it works. It's more complicated than that. It is the first function, as it is, times the derivative of the second, plus the derivative of the first times the second. So you got two terms, still multiplied together, but just the original function times the derivative of the second, derivative of the first function times the second. That's called the product rule, because you're multiplying. And then the quotient rule, f divided by g. The derivative of that is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And I think I may have written that backwards yesterday. I apologize. I think I did write it backwards. But this is the correct difference quotient. Sometimes people remember this by low D high, so low means the bottom one, D derivative of the top minus high D low, high the high one, top one, D derivative of the bottom one. So we've got all these nice shortcuts so far, and we're building up our list. And in section 3.3 now, we're going to find the derivatives of trig functions. We're going to start with the derivative of sine. What is the derivative of sine? And usually I like to show you the full proof of the derivative of sine. But we're kind of running behind, so I'm going to do an abbreviated proof of the derivative of sine. It's in the book, the ebook. It's also in the lecture videos from previous semesters if you want to see all the details, but you wouldn't ever be asked to reproduce that on an exam or homework or anything like that. But if you're really interested, it's neat because it does involve a lot of geometry. But what I'm going to do is that the limit as theta approaches 0 of sine of theta over theta is 1. If I just tell you that's true, then that makes the proof a lot easier. It's really in proving this that takes a lot of time and a lot of neat geometry, though. But there's a similar one we need as well. Limit as theta approaches 0 of cosine of theta minus 1 over theta equals 0. Again, there's a lot of geometry to prove this one. Check it out if you're interested in seeing the proof. It's pretty neat. This one takes a little bit of time, just some geometry though, but it relies on knowing this. But if I just tell you that these things are true, then I can show you that the derivative of sine, derivative with respect to theta, I'm letting theta be the independent variable. Usually we use that Greek letter theta for an angle. Excuse me. By definition, it's the limit as h approaches 0 of sine of theta plus h minus sine of theta all over h. That's the definition. You plug in theta plus h, normally an x plus h. Here are variables theta, so theta plus h. And then you subtract the original function, divide by h. There's a property from trigonometry that deals with the sine of two angles being added together. It says, right over here, if you've got the sine of A plus B, you could rewrite that as the sine of A times the cosine of B plus cosine A sine B. If you remember from trigonometry, there's actually a handful of formulas like this. There's one with sine being added and another one for sine being subtracted. And then there's a third one with cosine being added and a fourth one with cosine being subtracted. They're all very similar, but this is the one we need because what we have over here is the sine theta plus h. So we got two things here. If I compare to the a and b over there, I could say this is limit h approaches 0. Sine of theta, sine of the first, that's cosine of the second, cosine of h, plus cosine of the first, so cosine of theta, times the sine of the second, sine of h. Now, if I split this up into three fractions, actually just two fractions, I want to put these two terms together in one fraction because they both have a sine of theta. Limit h approaches 0. Sine of theta, sine of h, minus sine of theta, all over h, plus cosine of theta, sine of h, over h. So what I did was just took this, put it together with this, and wrote one fraction. And then this one, I left in its own fraction. H approaches 0. Both of these have a sine of theta, so I can factor it out. Sine of theta, cosine of h minus 1 over h, plus, I'm going to write this one a little bit differently, cosine of theta times the fraction, sine of theta, or sine of h over h. I can apply the limit to each term individually now. Sine of theta, cosine of h minus 1 over h, plus limit h approaches 0, cosine of theta, sine of h over h. Property of the limit. This sine of theta does not have an h in it at all, so it's not affected by the limit. It's constant with respect to the h anyway. So I can slide it out. Limit h approaches 0, cosine of h minus 1 over h. Likewise here, the cosine of theta is not affected by the limit. So I can slide it out. Cosine theta, limit h approaches 0, sine of h over h. And then if I just rely on these two statements being true, then I can say this limit is 0. Over here I got a theta, but here I got an h, but it's the same expression. So sine of theta times 0 plus cosine of theta. And this one, I assume this is true, that's equal to 1. Sine of theta times 0 is 0. Cosine of theta times 1 is cosine of theta. So left with cosine of theta. So the derivative of cosine, or derivative of sine is cosine. Derivative of sine is cosine. That's convenient. Derivative of that trig function is just another trig function. Derivative of sine is cosine. Derivative of cosine is, you might have a good guess even if you've never seen it before, but before you guess, let me remind you of something. A derivative is basically a slope of a tangent. So it's saying the slope of the tangent to sine is whatever cosine is at that particular value. If you think about the graph of sine, sine looks like this. Has a period 2 pi y equals sine of x. So if you imagine tangent lines, right at the beginning, tangent line kind of look like that. And it turns out that the slope there, you can tell from the picture, it looks like it's about 1. And cosine of 0 is 1. Now move a little bit further over. Tangent line there would be horizontal at pi over 2. And cosine of pi over 2 is 0. If I just continue on, you can see slope right there. It looks like it'd be about -1. Cosine of pi is -1. Actually, graph cosine might make it easier to see. This is cosine. At the beginning, slope of sine is 1. Cosine of 0 is 1. At pi over 2, the slope of the tangent is 0. The cosine of pi over 2 is 0. At pi, derivative of sine is -1. Cosine of pi is -1. And so on and so forth. So if you want to think about the derivative of cosine now, it's going to start off being 0. Sine of 0 is 0. But it starts off being negative. If I just move a little bit to the right, it's negative. Back down here, pi over 2, it looks like it'd be -1. So it can't be that the derivative of cosine is sine, but it's obviously related. The sine is positive, but these derivatives are negative. So, is anybody going to guess? I'm kind of taking the long way to get there. It's not sine. Huh? A good guess? But no.
Sine minus pi. Sine of x minus pi.
That might be true, but there's a simpler expression. Just negative sine. Just negative sine. Because there's a property of trig functions where you get, if you subtract pi, you're shifting it, so that it might be true. But this is the general expression that's used. Because, again, at the beginning of cosine, tangent line has a slope of 0. That matches up with sine. But then as you move to pi over 2, the slope is -1. Sine is +1, so negative sine would be -1. If I move to pi, the cosine, the slope of the tangent line there would be 0. Matches up with sine. Also match up with negative sine. If I move to 3 pi over 2, slope would be 1. At 3 pi over 2, the sine is -1, so it's the opposite of that. But anyway, here's what you need to remember. Derivative of sine is cosine, derivative of cosine is negative sine. Derivative of these two basic trig functions is just the other one. This one has a negative sign now. And then from that, we can derive all the others. Like derivative of tangent. To derive all the others, tangent, secant, cosecant, and cotangent, we do have to remember some identities from trigonometry. If you remember from trigonometry, every trigonometric function that's not sine and cosine can be expressed in terms of sine and cosine using some identity. Tangent. Did they remember how to express that in terms of sine and or cosine? Yeah. The other way to that, sine over cosine. Let's see. Cosecant. Do you remember how to express that in terms of sine and or cosine? Exactly, 1 over sine. And secant. 1 over cosine. The way I remember these is they're called co-functions of each other. You always got in these relationships here one of them that starts with the prefix co. Co-secant is related to sine. Secant is related to cosine. And then you got cotangent. And it's related to tangent as well. It's a reciprocal tangent, but that's not the one we need because we're trying to express it in terms of sine and cosine. What's this one, Ruby? Cosine over sine. So all 4 of these can be expressed in terms of sine and or cosine. So we can use that fact to figure out the derivatives of these. Because if I want to figure out the derivative of tangent, I could use the quotient rule. Likewise for all of these. Derivative of cosecant, use the quotient rule. So derivative of tangent is derivative of sine over cosine. And then by the quotient rule, you got a fraction of the quotient. Low D high. Low D high bottom times the derivative of the top. Low d high minus high d low. Sine derivative of the bottom. And then all of that over the bottom square. So now to apply the derivatives to these individual parts here. Derivative of sine is cosine. So I got cosine times another cosine. Sine times derivative of cosine. Derivative of cosine is negative sine. And with trig functions, when you have a trig function squared like that, there's kind of a convention that you write it like this. That way it's obvious it's cosine being squared, not the x alone being squared. Anyway, back to the top, I got cosine times cosine, or cosine squared. Then I got a negative sine times another negative sine that makes positive sine. And then, does anybody remember this identity? It's equal to 1, yep. Sine squared plus cosine squared is equal to 1, always. It's a Pythagorean identity, they call it. Because basically it is Pythagorean theorem. Anyway, that's always 1. And so basically this is simplified, but I can make it look better by using the fact that cosine and secant are reciprocals of each other. So I could write this as secant squared of x. So the derivative of tangent is secant squared. That's the final conclusion. Derivative of tangent is secant squared. The first one's super nice. Derivative of sine is cosine. Derivative of the second one here, derivative of cosine is negative sine. Pretty nice that we got that extra negative sign. Derivative of tangent, secant squared. So a little bit more complicated. Of course, it's a trig function here, still a trig function here. But it's not as simple as the first two, I guess. Anyway, next one. Derivative of cosecant. Cosecant can be rewritten as 1 over sine. So the derivative of cosecant is the same as the derivative of 1 over sine. And I could use the quotient rule again. Low d high low the bottom times the derivative of the top. Derivative of the bottom all over the bottom square. Now to differentiate each one of these parts individually, derivative of 1 is 0, because that's a constant. So sine times 0. 1 times the derivative of sine is cosine. I got minus cosine of x over sine squared of x. Sine times 0, just 0. 3 times 0 is 0, so I'm left with negative cosine over sine squared of x. So basically done, but I can make that look a little better as well. What I could do is rewrite this as negative cosine of x over sine of x times 1 over sine of x. Splitting that sine squared up. And then cosine over sine is cotangent, so negative cotangent of x. And then 1 over sine is cosecant. So there's the final expression. Derivative of cosecant of x, negative cotangent times cosecant. So it's even more complicated than the previous ones. Negative cotangent times cosecant. Again, the first one was really nice. Derivative of sine, cosine. So I kept going through here, they keep getting more and more complicated. But it is still derivative of a trig function is something in both trig functions. That's nice. Anyway, 2 more. Derivative of secant. Derivative of secant. Secant's 1 over cosine. So use the quotient rule again. Low D high. So the bottom times the derivative of the top. Minus I below top times the derivative of the bottom over the bottom squared, cosine of x squared. Just like over there, derivative of 1 is 0, it's a constant. Cosine of x times 0. Derivative of cosine is negative sine. That times 1, so 1 times negative sine is negative sine. So cosine squared of x. Cosine times 0 is 0. Minus negative is plus. So I got sine of x over cosine squared of x. But the way it's usually written, just to make it look a little simpler, I guess, is like over here I could split the cosine up into 2 separate fractions. And then each one of those fractions corresponds to its own trig function. Sine over cosine is tangent. And 1 over cosine is secant. So there's the final expression as it's normally written. Derivative of secant is tangent times secant. Derivative of secant is tangent times secant. Last one, derivative of cotangent. Cotangent. Cotangent's the same as cosine. Sine. So use the quotient rule. Low D high, so bottom comes the derivative of the top. Minus high D lows, cosine comes the derivative of sine. Over the denominator squared, sine squared. Sine. Derivative of cosine is negative sine. That's cosine. Derivative of sine is cosine. Over sine squared. And then I got sine times negative sine, so it's negative sine squared. Cosine times cosine, cosine squared. Had this in a previous one, but they were positive. It's Pythagorean identity. They're positive. So what I could do is I could factor out a negative 1. Sine squared plus cosine squared. Or sine squared. And then sine squared plus cosine squared is always 1. Maybe 1 times 1 is negative 1. Basically, I'm done, but the way it's often written is by using the fact that cosecant is the reciprocal of sine. So this can be rewritten as cosecant squared. That's negative cosecant squared. So derivative of cotangent is negative cosecant squared. That's the last one. Derivative cotangent is negative cosecant squared. All right. So those are the new derivatives in this section. What I did in class today was basically kind of derived all of these. You don't have to do that again. From here on out, if you're asked to calculate the derivative of cosecant, for example, you can just use this formula. It is now a formula that you can use for those derivatives, for all of these. You just use that formula. So of course they want you to calculate derivatives now with functions involving trig functions. So for example, number 2, section 3.3. Sine of x plus 8/7 cotangent. Find the derivative of this function. Using the prime notation, the derivative of f I'm trying to find the derivative of all of this. I'm going to happen. When I'm trying to find the derivative of things added together, I can apply the derivative to each term individually. So if I apply it to sine, I know the derivative of sine is cosine. If I apply the derivative to 8/7 times cotangent, the 8/7 is a constant that I'm multiplying by, so it slides through. Then I apply the derivative to the inner function here, with the function being multiplied by the constant. Cotangent. Derivative of cotangent is negative cosecant squared. So instead of plus 8 over 7 times negative cosecant squared, I can just write that minus 8 over 7 cosecant squared. So there's the derivative. I did it just in 2 lines there, but really there's a lot going on. I used a lot of properties to do that. Here's, I guess, kind of a nasty one. Number 5. Nasty in that it's got a lot of stuff multiplied together. It says the function is, or they've written y equals 7x squared times sine of x times tangent of x. So I really have 3 functions being multiplied together. 7x squared, sine of x, tangent of x. So I have to start with the product rule. Product rule deals with just 2 functions being multiplied together, but I could use it repeatedly for 3 multiplied together. If I do this slowly, instead of thinking of this as 3 functions, if I temporarily think of it as 2. There's the first one, here's the second one. The derivative by the product rule says the first function, 7x squared sine of x, times the derivative of the second, derivative of tangent, plus the derivative of the first, 7x squared sine of x, times the second. 7x squared sine of x. Derivative of tangent is secant squared. Then I got to do the derivative of 7x squared times sine of x. So I have to use the product rule again here. The first time I was thinking of that as just 1 function, but really it's 2 multiplied together. So the derivative of this is, this time this is one of the functions, this is the other. So it's the first, 7x squared, times the derivative of the second, sine of x, plus the derivative of the first, 7x squared, times the second, sine of x. But then all of this is being multiplied by tangent. So I'm going to put a set of brackets under all of this because it's all multiplied by tangent. So x squared, sine of x, secant squared of x, plus 7x squared. Derivative of sine is cosine. Cosine of x. plus derivative of 7x squared. 7 slides through. Then I could use the power rule to x squared, so the 2 drops down. I subtract 1. X 1 times sine times tangent. I'll move up here to finish it up. 7x squared sine of x secant squared of x plus, if I distribute this tangent, 7x squared cosine of x plus tangent of x plus 14, because sometimes you give me 14x sine of x times tangent of x. So there's the derivative. Now I might be able to rewrite that differently using trig identities, and that's fine, but not absolutely necessary. So this would suffice as an answer. But just to show you here quickly, in particular this one here, tangent could be rewritten as sine over cosine. So if I did that for that one, sine of x over cosine of x, then I can cancel the cosine. And there's ways to rewrite this, but nothing's really going to cancel. Likewise in this here, nothing's really going to cancel, not like in this middle one where something did cancel. I'll rewrite it. So there's another equivalent way to write the answer. All right, that's all for today. Have a great rest of the day, and I'll see you all tomorrow, and we're going to learn something called the chain rule, which is probably the most powerful shortcut. Anyway, see you all then.
Like I know that.